welcome guys. Yeah, so this is my real mathematical analysis video. So I want to build my own video list. Yeah, so basically follow the routine mathematical principle of mathematical analysis. Okay, so yeah, so let's start. So this video list should be very long, hopefully not super long. Okay, so this video basically talk about basic topology, and yeah, so I will skip a lot because I think this is a simple one. So basically just talk about some finite countable and uncountable idea. So maybe in the future in the set theory I will talk more. Okay, but in this video I talk a little bit. Okay, so I mean, so I don't want to start from the ZFC set theory system. So I believe that all you guys know what set is. Okay, and also if so, I can also talk about function from set A to B, and also if you give me some subsets of A, then I can write f of E. As if f of E is all f of x, where x belongs to E. Okay. And also, I think everybody knows about 1, and onto. So this is also called injective. This is also called surjective. Okay, so injective means that, so yeah, so this is just some preliminary. I think it's very important. If x is not the same as y, there should be difference. Okay, and the surjective means that for any y belongs to B, you can find x belongs to A, such that f of x equals to y. Okay, and also I also like to write, take subset of B. I like to write f inverse E. Basically, all the element x belongs to A, such that map into E. So this is the inverse image. Okay, and I pick any element y belongs to B. I can take f of inverse y. Basically, it's all element set into equals to y. Okay. Also, yeah. So this is just very basic idea. Okay. Also, equivalent class. I think if you learn about algebra, that people like to say about equivalent class. So I say A equivalent to B need to satisfy 3 conditions. So A, B, A, and also if A equivalent B, B equivalent C, hopefully you get this. So this is called equivalent class. Okay. Okay, so also given definition. So given any 2 sets A, B. Yeah, so these are very abstract. So given any 2 set A, B. So we say that A is let's see. So we say AB has the same cardinality, or has the same cardinal number, or they all have the same cardinality. That means there exists F, which is from A to B, which is 1 to 1 and onto, or people like to call it bijective. So basically, you can, for each element A, you can correctly identify into some element B, and conversely, since it's 1 on 2, so inverse is this. Okay, so for example, you have element like 1, 2, right? So it's cardinality mapped to 3 is this has the same cardinal number as 3, 4, because I can assign 1 to 3, 2 to 4, right? So you can obviously say that see that any set with any finite element, if they have the same cardinality, means that they have the same number of elements. A little bit stupid definition. Okay, so this definition also, let's say Jn to be 1 to 2 is a set from 1 to n. Okay, so we give 5 definition. So this is file routine, but I think it's very stupid. But I still need to write. So A is finite, means that A is if only if A ideal has the same cardinality for some Jn for some. Okay, and it's infinite. Okay, so let me define Z. Just the natural number be all the basically all the number, all the positive integer. So all the positive integer. So right. So this is a set. Okay. So if only if A has a same cardinality as integer. No, sorry. Sorry. I'm still. So A is infinite means that A is not finite. Sorry, I'm stupid. Yeah, because we will see that infinite contains a lot of other like real numbers or its power set. So keep it arbitrarily large. Arbitrarily large. Okay, so A is countable. So what do we mean by countable? Right? Countable means that A is has the same cardinality as a natural number. Okay, A is uncountable. If A is not finite, so A is infinite, and A is not natural number, right? Okay, so at most countable, so A at most countable. So at most countable means that A is finite or countable. Okay, so this is just some terminology. Okay. Okay. So I just want to trivial example. The first example is basically so suppose you are A, look at 0, 1, minus 1, 2, minus 2, 3, minus 3. Yeah, so this is just the integer, right? So you can map this as 1, 2, 3, 4, right? 5. Okay, so simple mapping is basically f of n. Right, so if n is even, it maps to n divided by 2. If n is odd, it maps to minus n minus 2 divided negative n minus 1 divided by 2. So this is z, right? So you can create this f from z to a, right? So yeah, show it by yourself. Okay. Yeah, so let's see some very basic example. Let's see some another definition called sequence. Okay, so sequence, I think everybody knows, right? So sequence can be viewed as the, right? So given a set A, I can, so if I say let's say xn is a sequence of A, so this means that there's a f, right, for each integer from z to z to A, such that basically for each fn should be greater or equal to 0. So usually it should start from the positive integer, or so f of n is just some element belongs to A, right? And people sloppy, so write xn. So for each index n, there is an element in A. So it's just a sequence of A. Okay. So obviously this is countable, right? By definition. Okay. So theorem. So infinite. So every infinite subset of countable. So every infinite subset of countable sets A. So countable sets meant can be viewed as just the standard integer, right? So every integer subset of n is countable. Okay, so proof. This looks very intuitive, right? But let's see. So you take E subset of A, and E is infinite, right? Okay, so I can, right? So A is countable, right? So I mean I can label A every element in A, x1, x2, right? I can count and label every element in A as x1, x2, x3, and keep going, right? Okay, so let me just construct. So I can construct, let's say, construct a set nk, right? Nk is such that so I choose n1 to be the smallest positive integer, such that xn1 belongs to E. Okay, so I think everybody knows the trick, right? So there are x4, x3, x5. Okay, so I keep iterating. So I pick n1 such that xn1 is a small, so I go left and I see the first element I see which belongs to E, and I pick I call it xn1. Okay, and I keep going and pick up xn2, xn3. So I get xn1, xn2, xnk, right? All these are basically belongs to E. Right, obviously that every element in E, right? Oh, since E is a subset of A, right? So all the element E will find its place. Okay. So so this is just the whole E, right? But by definition, I already label it as a subset of integers, so E is countable. Okay. Just let's do a bit stupid. Okay. Okay. And I think everyone knows about union and the intersection, so I skip the definition. Okay, the theorem. So if you have En from 1 to infinity, it's a subset. So every En is a subset of A. Okay. And okay, so basically you have some n from 1 to infinity set En such that En is countable for every n. And the theorem says that the union of n from 1 to infinity is countable. Okay, so proof. Proof is very easy, right? So I use xnk. So nk is nk, right? There are two label means that the case element of En. Right, so E1 has an element, let's say xn 1, 1, 1, 2, 1, 3, 1, 4. Okay, and E2 has a 2, 1, 2, 2, 2, 3, 2, 4. And the E3 has a 3, 1, 3, 2, 3, 3, 3, 4. I keep going, right? And you can say it's infinite, right? But it's fine. I can always count it. Okay, so the way that I count is I start from this one, right? So I count this one is 1, these two are 2, 3, and then these are 3, 4, 5, 6, and I keep going, right? Okay, but you might worry that there are some of them are the same, right? So we may overcount, but who cares? If I see somebody is already occurred, then I just skip, right? So which I prove that if everything's distinct, these guys are countable. If it's not distinct, then it's a subset of this, right? So I can freely just skip that one, right? So n from 1 to infinity En is countable. Okay, and so basically we also proved that so this is the corollary. Suppose A is at most countable. So at most countable means that it's finite or countable. So if A is at most countable, then for every alpha, let's say you belong to A, and then your B alpha is at most countable. Right. So basically, we proved that the union of the countable union of the countable set is countable. Okay. So hopefully you understand the union of the countable union of countable set is countable. So this means that this B alpha belongs to A is countable. Okay, so this is just what we already proved. Okay. Okay. So I think this is the same. This is also has a corollary that if A is countable set, so A is countable, then you can define a so-called Bn, right? So Bn can be viewed as A times A times A. So just some Cartesian product such that A1, A2 up to, okay, so up there total n of length An, Ai belongs to A. So this is countable, okay? Since we already proved that the infinite of length is countable, right? So finite of length must be countable. Okay, so from this we know that rational is countable, right? Because rational can be viewed as a subset of can be viewed as a not subset, but can be embedded into the Z cross Z. And you make the equivalent class such that A, B, C, D, right? So if you write A, B as A divided by C, C divided by D, such that A divided by B equals to C divided by D, if A, D equals to B, C. Okay, so we already proved this is countable, right? And the Q is just some natural class in Z cross Z. So which this guy is countable. So any finite set with the any set subset of the countable set is countable, right? So this is countable. Okay. Okay, so the final result is the Cantor diagonalization. So Cantor diagonalization says basically it says that the real number is uncountable, or basically 0, 1 interval is uncountable. Okay, and yeah, maybe in the set theory I will illustrate this, but I think here we only prove that we prove that the A, so let A be a set of all sequence whose element are digits 0 and 1, then A is uncountable. Okay, so that means every element in A looks like 0, 1, 0, 1, and it must be infinite. Okay. And yeah, and we bound prove that all these guy forms a set A, which is uncountable. Okay, so proof is basically use the diagonalization idea. Okay. Okay, so the diagonalization idea just by contradiction, right? So suppose A is countable. Okay, so if A is countable, then I can just label A, right? So I can label, let's say I label 1 first element, call it R1, R2, and I label second element 2, basically call it sorry, maybe that's for the first one, maybe I call it A1, A2, and then for second one I call it B1, B2, and then for third one I call it C1, C2, and all these labels, AI or BI or CI or whatever I is all 0, 1. Okay, so suppose you already labeled it, then I claim that you missed something. Okay, so I can create number X. So if A1 is 0, I let X1 to be 1, right? So this is not A1. Okay, if B2 is 0 or 0, and I choose this guy to be negative B2, so B2 will be this guy will be 1. If B2 is 1, I pick up 0, and I choose, if C3 is 1, then I choose this third position is 0. If C3 is 0, I choose C2 1. So it's not C3. Oh, by the way, this is not. So not A means that if A is 0, I choose 1. If A is 1, I choose 0. Okay. So obviously that X is not the same as 1, right? Because the first one is not the same as this. And X is not the same as 2 because this guy is not the same as 2. And X is not the same as 3 because this is essentially. And this can do infinite, right? Because you say that you have infinite of them, right? Okay, so contradiction. So uncountable. Okay, so basically for real numbers, if you want to prove you can use this to prove that 0, 1 interval is uncountable, right? Because every element in X in 0, 1 can be used as binary, can be represented as a binary representation. So basically, right, you can write any element X belongs to 0, 1 into a summation of AK 2 to the K, K from, I think it's from 1 to infinity, and AK is 0 to 1. Right, so you have the fractional binary representation for each X from 0, 1. So you can use, so obviously from this, you can say that 0, 1 is uncountable. And the one, okay, so idea is that once you prove 0, 1 is uncountable, then you can write a map function. Okay, you can write a function from 0, 1 map to, I think it's what? You can map is arctangent X, right? So let's say you want to find a map from 0 to 1 to R, or basically let's maybe do the other way. So maybe that's R to 0, 1, right? So or make it -1 to 1, and you can define your f to be f of x to be arctangent x, and 2 divided by pi, right? So if x goes to infinity, then this f of x will close to 1, right? So if x goes negative infinity, -1, right? So this looks like this. So this is 1 minus -1, right? So from this picture, you see that this f is 1, 1 and onto, right? Okay, up to the 1 and -1. And I already proved that besides from this one point, I already proved that the subset of this 0 is uncountable. Right? So obviously the cardinality of rationals should at least greater or equal to the subset, right? So which disprove that the real number is uncountable. Okay, so see you guys next video. Next video we talk about metric space.